In the beginning, science and religion held hands, kissed one another like old lovers, and danced into the darkness. Bang! The first few seconds of the universe, all the matter that would ever exist in the universe was condensed into something the size of a pea. Nothing could take this pressure and still remain physical, so everything in the universe was energy, a corrosive cloud of energy that ate at the nothingness around it and expanded at light speed, pushing away from itself, to get away from itself, to make space, and in its wake it created distance, it created time, and it created a space for itself to cool off. Now as the universe began to expand, as it continued to expand, this energy was no longer packed quite so close together, and out of this cloud, things started to condense. Small things, constituent things, the building blocks of all matter, leptons, quarks, bosons, fermions, these things condensed out of here like ghosts. And as the universe continued to eat away at the nothingness and continued to expand, these things condensed again to create electrons and protons and neutrons and photons. And as the universe cooled even more, these things banded together to form the most common element in the universe, hydrogen. Now, chaos is not uniformity, and this early universe was not a solid flat sheet. It was lumpy, it was bent. There were parts of the universe that had more hydrogen rather than less. And the first rule of this new universe is, he who has gets more. And gravity sent out its tendrils and began pulling neighbors towards one another. Now those areas that had more hydrogen than the surrounding areas called in more hydrogen. And as these gathered together and spun, parts of it got dense enough that the hydrogen started bumping up against other hydrogen and collecting together. And it was kind of reverse of the Big Bang, things coming together. And they started bumping so close to one another, hitting up so close to one another that eventually their own mass pushed two hydrogen atoms together, creating helium and releasing heat and light. Bang! This was a Class O star that lit the universe that had been dark up to this point. Now these stars are brilliant, bright white. They extend out their light and they burn so fast and so hot. Hydrogen, hydrogen, helium, hydrogen, hydrogen, helium. But it only goes on for a few million years. But while this is going on, it spews out a cloud of photons that push back against gravity. Now as gravity pulls, it calls more hydrogen in. The solar winds push all of this hydrogen coming out, and you end up with something like a balance. But this doesn't last for very long, because eventually the inside of this star starts getting old, starts getting weary. It doesn't have hydrogen anymore in great quantities. What it has helium, and it starts the second phase, which is taking helium and trying to smash them together to make boron or lithium, or these things together to make oxygen or nitrogen or carbon. Now, atoms have a sense of self, a being about themselves. They don't like being pressed together. So the heavier elements aren't as useful to a star. They don't burn as quickly. They don't burn as brightly. It makes less sense for them, and they resist it. And eventually what happens is the star gets too old, and the battle between gravity and the solar wind starts losing, and gravity starts winning, and it pulls more things in, and the star gets heavier and heavier. And eventually, the core of this star is filled with older elements, and the whole thing collapses, changing as much hydrogen as it can into helium, and helium into heavier elements. And it collapses again until most of the core, these heavier elements, stopping at about carbon, which is the least useful of the elements as far as energy is concerned. And then what happens next depends on how heavy the star is. If it's a star about 3 times heavier, or a little bit less than our star, then what happens is it tries condensing again from carbon down to iron. And it can do that. It can make that leap, but the next step is tougher. It tries to condense iron down. Now iron doesn't want to be condensed any further, and at that tight a density, the electrical force in the atoms overcomes the force of gravity, and in the space of less than a second, the entire star explodes. Bang! This is a neutron bomb that will extinguish life in solar systems hundreds of light years away. one of the reasons we may have been given the chance to evolve is because we're not located near dense factories of stars. We're located out on the lazy arm of the Sagittarius in our galaxy. And maybe because of this, we haven't been sterilized enough to wipe out life, giving it a chance to have foothold. Now, what if it's not that heavy? What if it's heavier than the sun by more than 3 times? What if it's a really large star? Really large stars try the same thing. As they get too heavy, they condense. They condense down to carbon. They condense down to iron. But this time, gravity is stronger than the electrical force. And what happens is it tries this one more time, and it condenses from iron down. Now, when it makes this final step and it doesn't explode, gravity takes this star and it bends space around itself into the shape of a vase. It pulls the very universe out of alignment, and it creates a hole from which supposedly nothing can escape. Now, gravity can still make it out, and this black hole will reach out across light years, and it will grab other stars, and it will drag them to itself. The Hubble telescope, which orbits our planet, can see into the distant space and thus time, and we can see stars being pulled into black holes. And with the right detectors, we can hear gamma ray screams from these things before they disappear beyond the event horizon. Now, we have geniuses, and they have said that nothing can escape a black hole. And it doesn't seem to be true. But as near as we can tell, anything that goes into a black hole will never come out within the lifetime of anything reasonable. But this is not the end. Those stars that were smaller, they went supernova, or even smaller than that, where all they did was spew all the things. Think of what they were doing the entire time they were there. They were a factory. They were an assembly shop. They were taking elements and building heavier elements. Now, when the star explodes, it leaves a section of space seeded with the things it made. The carbon, the oxygen, the nitrogen, the helium. And it takes these things and it starts the whole process all over again. These things start collecting. As larger lumps collect more to itself, gravity begins pulling things to itself and bringing them together. And once again, atoms are bumping up against one another. Now this whole thing is moving through space, and as it's spinning, some of the lumps form around it, forming permanent falling patterns, orbits. Now, these won't become a sun necessarily. The center one will, but the ones around it will become smaller planets. When this star lights, it won't be the brilliant arc-white blue light of an O-series first-generation star. It will be a different color, maybe a yellow star like our own, a G-series star. Or maybe it will become even a red star or a brown dwarf, flickering with just enough energy to be barely visible. Now, the smaller lumps, those will form planets. What happens to them depends on how close they are to the planet and how bright and how hot this new sun is. Those planets that are too close to the sun will have whatever water they have boiled away, their atmosphere blown off or burned off by this sun. Those that are too far away will only have water in an ice form, will never make it to actual liquid water. Now, astronomers refer to something called the Goldilocks zone. It's a distance, depending on how bright the star is, between which you can have an atmosphere and you can have liquid water rather than just frozen water. These planets are composed with things built in the first generation star. And on these planets, in the Goldilocks zones, you have everything you need. You have water, you have carbon, you have oxygen and nitrogen, and just maybe, if the chances are right, you might have, bang, life. Everything on Earth, every organic thing on Earth uses carbon as the backbone for its very existence. From the smallest AIDS virus to the most towering sequoia to the greatest beasts that have ever lived in our oceans. All of these are based off of carbon. Every cell in your body is composed of elements that were birthed in the star, a first-generation star, and cast off when it died. So, when I tell you, you are the children of stars, I'm not being poetic. The neurons in your brain have danced on the coronal skin of a first-generation star. The iron in your blood remembers when the Earth was molten and smashed by asteroids and rocks from space. The nitrogen you breathe, that has been breathed by every living thing since the dinosaurs roamed, that remembers the cold distances of space in between the birth of stars. So when I tell you, you are the children of stars, I'm not being poetic, I'm not exaggerating. What I'm doing is telling you the truth.